Okay, so right here, we're going to have a quick overview of our code and the code we wrote for this hackathon. That is the kind of important part. Hackathon is the kind of in the name. It is about the code. So we'll go over that quickly and just show you, I guess, what we've done, where we started, where we got to, and how that all worked out. So starting out real quick, this is our first file we worked with. This was just kind of reading the data. This was playing around with it. We ended up reading a lot and trying to figure out what we could do with these specific columns. This was a lot of trial and error, again, as data science and data analytics tends to be. You really got to look through it and play around with your data to know not only what you can do, but what you actually have given to you in the first place. So here again, we're just printing out the columns. We're printing out the head of a bunch of different data frames. We start adding in some of our own custom columns and features here, and writing our data pipelining functions so that we can then later on in a more dynamic fashion add that into our code, whether it's being fed into a deep learning model or a scikit-learn regressor model. Jumping over here, we now have the first checkpoint we reached. This was the first time we were able to use the dense model, the fully connected deep learning dense model, to actually train a network, to train a model. My apologies. So again, this one used far less variables, far less features. This was more simple, just taking the average temperature and seeing how well this model could predict, just taking the average temperature over all of the cities and correlating that to the current temperature. And our final result was around the 3,300 megawatt accuracy mark. So again, that was just the current weather average between all the cities, correlating to the current energy output. Next, we got to our second checkpoint. This was where we started implementing more of our own custom functions and custom pipeline functions adding to the data frame. So as you can see, we're producing data with nulls as we add a bunch of rolling averages. We actually ended up having, I believe, 42 columns in the data frame. So starting out from the initial, as you can see, initially we simply had 12 columns. To jump to 42 meant that we added a lot of custom features and did a lot of custom analytics onto this data frame. So here adding stuff like the hour, day, and month flag, as well as the year, that giving the model and the predictive power, depending on what we were doing, a little bit more spatial relative information on the time series and what it's kind of fitting in. So now if I jump down, you can see again, we have our errors here, of course. So this is just where we ran into some issues, but a lot of our code, this was again just a bit of a proof of concept piece. Next, we come into the first of the final pieces of our code. So these are the exciting files. This is the first of the exciting files, if you would like to call it that. So these are the ones that are actually producing some results, and this is our file containing the code going over the scikit-learn data models or machine learning models. So again, we read in our data frames. We then have to merge our data frames down here. We convert the data into a date time format so we can look at it as a date time stamp and to sort the data accordingly. So we merge our data, we run it through a custom pipeline. There are a couple, so prepare with pipelines. Again, lots of pipelines there. That's just pushing all the data through and in a dynamic fashion, adding these extra columns onto the data. So again, if I scroll through, as you can see, there is a lot more than was initially in the data, because we found some of our own custom flags to be useful, as well as a strong correlation between some historical information that they would have access to. So potentially certain loading information a week behind or other things like that. Next, we can go in here, we can see each of the models that we've been running. So the first one here is again our most effective model, which was the random forest regressor. And going down here, we can take a look at the accuracy, so being about 876 megawatts for this specific run. That does change, with time and how the model is generated. Again, it being a machine learning method, it depends how the algorithm or how the model, apologies, learns over time and what that looks like. As well as we've printed out here our correlations of each of the features. So we can see that the average hourly usage over the past 24 of this specific day, uh, meaning this specific day, meaning this specific kind of Wednesday or Thursday or something, actually is the strongest correlation to the output. But we can see here that all these are how all these variables relate, and we can see that they are all significant to the output um, in our random forest, which we found quite interesting because not only does this provide information about how to actually predict the total grid output, what it does is it also gives some information on some of the factors that impact the electrical demand, as well as how much they might impact it, which going above and beyond kind of just providing them a way to optimize their grid right now. Being able to know what causes demand on your electrical grid allows you to perform better long term strategies. It means that when you're planning for the future and you're developing a long term business strategy, you can tell that if, say, population is growing, or if the climate is changing in a certain manner, or if certain things are occurring, how will that affect my electrical grid and my electrical demand, not 2 years down the road, not 3 years, but maybe 5, 10, 15, 25, as some of these electrical assets do last that length of time. Uh, they can't be put up in a day. So allowing these companies to perform these long-term strategy analyses is also a very, very valuable tool and a very valuable resource to any of these companies. So then jumping down here, as you can see, we also have our other forms of regressors. These are the other ones that are talked about in the video, along with their predictive accuracy. So again, we can just see that the random forest outperformed all the other regressive models, meaning that in the end, we recommend a random forest model when predicting the total electrical demand at a specific time. Next up here, we just have our renewables network. So this was the code that focused around taking the current and past weather information and predicting the output of renewable energy sources on the electrical grid. So this could be very useful because this is what allowed the ISOs to then lower their margin of error by allowing them their margin of safety they need on their electrical grid when using these green energy sources, because it meant that it could give them more confidence about what these assets would produce at a given time. This meant that if they knew the electrical demand, if they knew what these assets would produce, they could minimize the amount of other energy they had to produce using less environmentally friendly means. So again, jumping through here, when we did this, we did the same thing, pulling all the data in, running it through a pipeline. Again, a pre-processing step. So I guess I skipped over that in the last one, but this is again using some machine learning best practices to normalize and standardize our data, just so that we're not feeding it in extreme outlier points, or we're not feeding it in data that is kind of scattered throughout the place. It's all centered around a little bit of a location, meaning that the absolute value difference between two different variables can actually be compared, because it can get tough to compare certain variables that are far apart on the absolute value scale. As you can see, jumping down here, we run through all this code with our data to pre-process it, but we ended up getting it into the format where we could then train a model on the code, on the data, apologies, and producing a mean absolute error of 920 megawatts of the electrical production. As well as jumping down here, we can see that our accuracy, at least for this run, being 750 megawatts using a random forest regressor to predict the output of the renewable source. So this code can be dynamically used to either predict for any renewable source there is. So in this case scenario, we've had one that's been run through, but the benefit of this is it would allow the ISO, if there's potentially a new renewable energy source they're using in the future of some sorts, maybe even the far future, one that we has not been discovered yet or something. You never know. It would allow them to then train a model on that data, and to dynamically set a new one depending on what they're using. Finally, we come to our TensorFlow version of the model. So this is again just predicting the overall electrical demand using a fully connected deep learning dense neural network. So here we have the batch size hyperparameter. We have here, we load in the data again, the same thing, merging it, pipelining it, piping it through, where we're able to get this fancy looking data frame. It's quite long, but kind of is what it is when you're performing deep learning, right? We pre-process our data. Again, just some best practices here. Here's our actual model itself. The initial thing we always do is we seed the environment so that the random state of all these occurrences and how it's generated is as standardized as possible, meaning that while the model might learn in a different manner, they're all set up initially. They're all initially set in a similar means, meaning that when we run our model, it gives us a little bit more knowledge of when we try and compare different approaches we were doing. From here, we just have a dense layer of our network, a simple dense layer, and the model itself, which goes through, gathers the inputs, iterates through creating a dynamic hidden layers with dynamic node sizes in these hidden layers to then go through and generate our model. One of the key features we used for generating our model was we used dropout layers to try and limit how much um, overfitting that our model had, but that was just a key feature there. Next, we just have some of our training and graphing functions. Then jumping down real quick, again, this is all the rest of the code here, just showing everything. Next, we have our model actually being trained, and we can see the accuracy and the results of this model producing a average accuracy score of about 1800 megawatts. Okay, so that is our code.